Right, good day to everyone. This is Rico de la Peña, part-time professor from Mapu University. And these are the water resources lectures for the water resources module of the geology resources course. And this series of lectures will cover the following topics like reservoir dams, sedimentation, storage capacity, potential dam site locations, and then we will move on to the aquifers and wellfields, including wellhead protection areas, and then we move back again to the water resources in the Philippines, such as the water use and water body classification and use, and finally the status of water resources in the Philippines. Now moving first to the reservoir dam. These are structures or impoundments with multiple purposes such as water supply, flood control, electricity generation, navigation, and recreation. Be more familiar with the dams, these are the different parts. The face is the exposed surface of the structure, which can be made of concrete, rock fill, or earth, and it has upstream and downstream faces. So the upstream is the one that is facing the reservoir, and the downstream, of course, is the one that's facing the downstream side. Another part is the abutment. These are essentially the sides of the dam that are in contact with the valley walls or canyon walls. And the naming convention here is we look from upstream to downstream, and whatever is on the right is the right abutment, and whatever is on our left is the left abutment. Another part here is the crest of the dam or the top of the dam, and this might have a road for access purposes and inspection purposes. Another part is the toe or the intersection between the downstream face and the natural ground surface. Another important part here is the spillway, which allows excess water to flow past the dam in a safe manner. By safe manner, we were talking about the water not being too erosive, right? So once you are conveying water at high velocities, you get more erosive power. And what the spillway does is it typically has a rough surface, like the steps, as you can see in the figure in your right. It has steps which induce turbulence on the water. And the turbulence, as you can see on the animated GIF on your left, actually dissipates energy of the water that is being spilled out from the dam. Next is the parts of the, or rather the locks. These are essentially like elevators, and they allow passage of vessels through the dam. As you can see in the figure, you have a vessel entering the lock chamber, and once it enters the chamber, the water levels can be lowered such so that the vessel can actually continue to the lower river level downstream. Now, there are four main types of reservoir dams: gravity, buttress, concrete, and earthen embankment. The gravity concrete dam basically relies on sheer weight or mass of concrete to hold back water. In consequence, it requires a massive amount of concrete, and the examples here are the Grand Coulee Dam in USA in your left, and the Ipo Dam in Bulacan on the top right figure. Another type is the concrete arch dam. This one relies on an arching effect to transfer all or most of the load from the reservoir to the solid rock abutments. Alright, so you have an arc, and the force of the reservoir is actually being transferred from the dam into the rock abutments. So it requires less concrete, but in here you actually need a strong abutment side, like typically solid granite or solid gabbro bedrock. And the examples here are the Vahont Dam in Italy on your left and the Hoover Dam in Colorado, USA on your right. Another type is the buttress dam, and it's actually similar to gravity concrete dam except that it has additional supports placed on the downstream side of the dam. And it actually requires less concrete compared to gravity concrete dams. And as you will see or you will note, the supports actually distribute the force exerted by the dam on the foundation. So it means that you can actually place this type of dam on foundations that are actually considered too weak to handle a gravity concrete dam. Examples of this type is the Rosalind Dam in France, as you can see in the left, and the Bartlett Dam in the USA. Earthen embankment dam is the most important type of dam, and it relies on earth materials, typically more than 50% by volume is just earth material. And its main part here is a clay core or a low permeability material in the core of the dam to hold back or control the seepage. These types of dams are most economical in small watersheds or in broad valleys. And also know that about 80% of all the dams in the world are earthen dams. So this is the most popular type of dam in the world. Examples of this type of dam is the Angat Dam in Bulacan, as you can see in the figure in your lower right, and the Proser Creek Dam in California, USA. Now, going on to the reservoir storage. All right, so dams are impounding structures and they basically store water. And there are key components, storage components. Okay, first component is the dead storage. And dead storage is basically here to store sediment or sediments coming into the dam. And you can see this zone or the dead storage component as zone 0 in the figure on your right. And then the next component is the active storage, which is related to the main functions of the dam, such as water supply, power generation, and so on. As you can see, this component zone is the zone 1 and zone 2 in the figure. And then you also have your flood storage, which is zone 3 and zone 4 in the figure. Now let's talk about the Alright, sorry. Dead or inactive storage is the capacity reserved to account for all the sediments that will accumulate at the reservoir through its anticipated life. So you're looking at least 50 to 100 years of life of the reservoir, And the top boundary of your dead storage is determined from either the elevation of your invert of the lowest drain outlet or from the conditions of the operating efficiency for hydroelectric turbines. So by optimal, we are talking about not too high or not too low. If the height is too high, it results in turbulence, which results in energy loss. And too low means that you might be reducing the energy potential. Now let's talk about the active storage, which is all about the water to be used for water supply, irrigation, navigation, recreation, and hydropower generation. As you can see in the figure, this is a schematic of a dam, and on the leftmost part is the reservoir, and from there, from the active storage part, the water enters the intake to the penstock, and the penstock conveys the water to the turbines. The water then spins the turbines, which then allows the generator to generate electricity. And finally, the flood storage component is, and it's actually mostly empty unless you have a flood. Flood storage is divided into two parts. First is the flood control pool, and second is the surcharge capacity. The flood control pool is the lower part, and together with the lower outlet, they handle the design flood or the largest floods that won't cause overtopping and other smaller flood events. The upper part then is the surcharge capacity, which in tandem with the spillway handles the extreme flood events. So what you're seeing here in the GIF is essentially a spillway. Okay, so it is handling extreme flood events in tandem with the surcharge capacity. Another part of the dam is the freeboard, which is basically just the difference between the maximum water level and the crest of the dam. This extra height is meant to provide protection from wave action as well as protection from overtopping. The overtopping is essentially water that's going over the dam, and this can be dangerous because it can erode the downstream part of the dam and subsequently cause leaks and eventually destabilize the whole structure. Now, we can also talk about the safe yield in reservoir storage. Safe yield is also called firm yield, and this is all about the maximum water supply that is consistently available from the dam. And this number can be estimated from historical streamflow records. We also have another term called secondary yield, which is any amount greater than firm yield. On the figure is the schematic of the Angat Dam or the Angat Dam system. So you essentially have your Angat Dam reservoir in Bulacan. And this reservoir is actually being supplemented by another dam called the Umiray Diversion Dam. And it's interesting to note that the Umiray Diversion Dam is actually residing on a different watershed. So this dam is on another watershed, and it's actually contributing water to the Angat through the Umiray Angat Tunnel. Now you have a secondary dam, which is the Ipo Dam, which is aiding the redistribution of water to the other water supply components like the Novaliches Diversion Weir and the La Mesa Reservoir, which caters to most of the Metro Manila. It's also worth noting that the La Mesa Reservoir also takes water from another dam, which is the Alat Dam. Alright, so that shows the big picture of the Angat Dam Reservoir system in Metro Manila. Now let's move on to the reservoir sedimentation or the method to estimate reservoir sedimentation. We will be talking about the concept called the trap efficiency. Alright, so note that dead storage should account for sedimentation that is good for 50 to 100 years. So you are talking about 50 to 100 years worth of sedimentation when you're talking about dead storage of a dam. And to estimate that sediment, we can use the factor or the number or the factor called the trap efficiency. This number estimates the percent of sediment that will be retained from the amount of sediment that is entering the dam. Basically, the higher trap efficiency, the higher sedimentation, and higher sedimentation is actually worse for the lifespan of the dam. Now, TE is essentially just sediment that is retained divided by the sediment that is entering the dam in percentage. Alright, now we can estimate the trap efficiency or TE from empirical equations like the USBR, the Brun, the Brown, and the other equations from other authors. Just note that the typical usage here is we start first estimate the trap efficiency or the percent that of the sediment that will be retained, and then we collect data of how much sediment is entering the dam or will enter the dam, and from there we can calculate the amount of sediment that will be retained by multiplying the amount of sediment entering the dam times the trap efficiency. Alright, from there you will get the amount of sediment retained in the dam, and then just multiply that amount by 50 years or 100 years, and you will essentially get the amount or total amount of sediments that will be entering or that will be retained by the dam throughout its lifetime. And you should design that in the dead storage. Here is just a chart or a curve that is used to estimate or predict the value of trap efficiency. So this figure was originally developed by Brun in 1953 and was later revised by the USBR. If you will look at the figure, the y-axis is the trap efficiency in percentage, and the x-axis is a ratio. Okay, so the x-axis is the ratio of the storage capacity or the total storage capacity of the reservoir to the average annual inflow volume or the water inflow. So this means that the higher the water inflow that's entering the dam, you essentially can get lower trap efficiency. So you can imagine that when you have a high water flow, you're essentially flushing in the dam easily, and it's easily flushing out all the sediments as it flows. Now, if you look at the right side, generally the larger the storage capacity of the reservoir, the higher the trap efficiency. So you can imagine that a big dam, all right, so you have a big dam here, and you have relatively low inflow rate of water. So you can imagine a big dam with a relatively stagnant water can trap a lot of sediments, hence the high trap efficiency. Now, just for future reference, these are the different equations used to estimate the trap efficiency. These are suited to different situations like small watersheds, large watersheds, and so on. Okay, but I won't be discussing this in detail. Now let's move on to the active storage capacity of reservoir dams. All right, so we're done with the dead storage. Now let's talk about the active storage component. Active storage, the main purpose of active storage, of course, is for more water supply, and of course, the storage acts as a buffer. All right, if you can imagine the active storage of the dam as your water drum in your household. So when you are anticipating a water supply cut off by Maynilad or Manila Water, you basically have to prepare your water drum and fill it with water. So that's what active storage is essentially doing. All right, so you prepare the active storage of the dam for the dry periods that will be experienced by the dam. Okay, so note that in dry seasons, we typically have a deficit, meaning there is more water that is being drawn out of the dam than is the water that is being supplied into the dam by the watershed. And note that deficits can last for more than 2 months in dry seasons. So if you are talking about active storage, uh, you should at least prepare for more than 2 months worth of water deficit. So the method in reckoning or calculating the deficits is we tend to view the deficits not on a month by month basis. We tend to view it on a cumulative basis, which we will see later in the next slide. This is the Rippl 1883 method or the mass curve method. This method is used to determine how much active storage capacity should be designed for the dam. What happens here is that we are trying to calculate the largest cumulative water deficit that the dam should prepare for. So meaning it tells you how big should your drum be, all right, to prepare for the water shortage that the dam should handle. Sorry. Now the steps are as follows. We start with inflow data and demand data, or maybe demand projection of how much water will be anticipated, all right, in cubic meters per second. And this is typically a data set for 24 months. So we have a data on how much water is going into the reservoir how much water can go into the reservoir from the watershed in cubic meters per second. And we also have a demand data, or like how much water will be taking is projected to be taken out of the dam in cubic meters per second. Now from there, we obtain the monthly volumes of inflow and demand, so we convert it from cubic meters per second to cubic meters or cubic meters per month. And then the next step is to obtain the cumulative volumes of inflow and demand. So by cumulative, we just add the sum from the previous months and all the preceding months. And then from there, we subtract the cumulative volumes to get the cumulative deficits. Basically, we subtract the the cumulative demand from the cumulative inflow. And from there, we can find the largest cumulative deficit. And this largest cumulative deficit represents the total amount of deficit that may span a couple of months. All right, so you can have a like 2 5 months of deficits, and the total of that is largest cumulative deficit, and that will be the basis of your active storage capacity. This is an example of a 24 months of inflow and demand data. As you can see, you have, for example, in month one, you have an average water inflow rate of 1,450 cubic meters per second. And the demand from the households, industries, and agriculture is around 1,600 cubic meters per second. All right. Now from there, we calculate the volumes per month, which is not shown in the figure. And once we have the volumes per month, we then calculate the cumulative volumes. As you can see in this figure, all right, so you have months 1 to 24, and here are the cumulative numbers. So basically, in the first month, this is the volume for month 1, and then for month 2, you basically sum the volume from month 1 and month 2. And then month 7 is about the volume for month 7 and all the preceding months. All right. Now from there, you subtract the demand from the inflow to get the largest cumulative deficit. And from here, we can see that the largest cumulative deficit is negative 0.44 times 10 raised to 10 cubic meters. All right, so the active storage capacity should be designed for a uh, so this is incorrect. Sorry, this is an incorrect number. It's 0.44 times 10 raised to 10, which is around 4 billion cubic meters. Okay, so sorry, ignore the number here. This is wrong. The the active storage capacity here should be 4 billion cubic meters. Okay, 4 billion cubic meters, not 400,000 cubic meters. All right. All right. Let's talk about the important assumptions of the Rippl method. First is that the data, or be it actual or projected data, in the given period will keep repeating in the future until the end of life of the reservoir. So for example, what we used in the example is a 24-month period worth of data. So we assume that this 24 months of data is representative of the 50 to 100 year lifespan of the dam. So this is a big leap of faith here. We are just using 2 years of data to represent what will happen in the dam within 50 to 100 years. Note that if the actual conditions have a bigger deficit, we will end up with a deficit that will carry over the years, and we may end up with a water supply shortages in the future. So does this sound familiar to you? All right. So if if you underestimate the deficit of the dam, of course this will carry over years and years and years, and you will be fucked up in the long term. So in practice, the driest periods are used in order to anticipate the largest deficits, which should be designed for in the storage. Now let's move on to the potential dam site locations. So note that we discussed the dead storage and the active storage, but we skipped the flood storage component of the dam design. So I leave that topic to the hydraulic subjects or whatever subject you will be taking. All right, so the focus here is on the resources. All right, potential dam site locations. This is a case study in Marinduque by Fesalbon and Blanco in 2019. So this study is all about the use of remote sensing data to narrow down potential dam sites in Marinduque. So note that dam projects are all about economics. So you have to satisfy the water demand, you also have to meet the electricity demands, and that those demands should be, or rather the benefits of satisfying those demands should be more or less profitable. All right, which of course depends on the site conditions. Like certain site conditions might require or might be cheaper to put an embankment dam. Certain sites what you might want to put a concrete gravity dam. So I just want to say that this study is of course is just a sort of a filtering. They're just pre-selecting sites here. All right. So the other site conditions that may modify the feasibility of a dam are not accounted in here. Now here are the some other considerations that we generally use when we are looking for dams. So deeper valleys, all right, allow higher dam heights. Higher dam heights mean we can have a higher drop in elevation and we can generate more electricity from them. Narrow valleys, of course, they require less construction materials. And then flat bottom valleys allow larger storage capacity. And then high inflows require less storage capacity and are less prone to sedimentation. So note that these key considerations, depending on the objectives of your project, the priority of these considerations may change. Alright, so additional context for the study. In the Philippines, we have our Republic Act 9513, or the Renewable Energy Act of the Philippines of 2008. So this act favors and subsidizes renewable energy. All right, so practically speaking, most of the renewable energy projects in the Philippines are subsidized. All right, and this actually sort of inflates the cost of electricity here in the Philippines. But I won't be discussing why. I mean, that's just how it is. Anyway, due to the low supply and high and rising demand for electricity, we have expensive electricity here in the Philippines. And the study of Fesalbon and Blanco is all about making it more accessible. I mean, making a they're they are targeting the or they were trying to formulate a method that would make it easier to find potential dam sites in terms of raw capacity. So the scope of the study is just about pre-feasibility studies for hydropower development. Okay, so their method is applicable for the stage that you do before a pre-feasibility study. All right, so whatever dam sites that you find from their methodology, you have to further filter them out. And the main data used here is the interferometric synthetic aperture radar, or the IFSAR, with 5-meter resolution. And they use two main criteria to find potential dam sites. First is the valley determination, and second is the flow accumulation. Mm. So, for additional context, Marinduque is a hilly and mountainous area. It has a typefall rain climate where you have more or less rainfall happening throughout the year. And in terms of electrification status, Marelco indicates that 388 out of 408 of the potential sitios are energized as of 2017. So they're more or less nearing their completion already. So this is the first criteria that they applied to find potential dam sites. So they looked for valleys using the IFSAR dataset. So note that valleys are the conducive landforms to place dams. And in the study, they used multiple methods to find valleys from the topographic data. They used multi-resolution valley bottom flatness, topographic position index, valley and ridge detection, and finally the geomorphons. And long story short, they found out that the most consistent method, or more or less the most accurate method for looking for valleys, was the geomorphons method. So it matched what they found in their manual delineation of valleys from the satellite imagery. Note that the geomorphons method classifies terrain morphologies such as valleys, peaks, ridges, spurs, hollows, slopes using image recognition techniques. And this method can be implemented in the GRASS GIS. The second criteria that they applied is the flow accumulation. What they did here is that flow accumulation is more or less the proxy for the base watershed area of your potential dam site. and they set the minimum flow accumulation as 100,000 cells. So if you multiply that by the IFSAR resolution, which is 5-meter resolution, so square the 5 meters, you have 25 meters. Multiply it by 100,000 cells, so you have 2.5 million square meters of drainage area. So that was their minimum criteria for the flow accumulation. And you can see here in the figure how the flow accumulation algorithm works. So you essentially just look or compute the flow directions of each cell and then count the number of cells that end up on a certain position. So in this figure, you have your cell at the bottom right. It has 35 cells accumulating on its point. All right. So all in all, they selected potential dam sites based on the presence of valley landforms and minimum flow accumulation of uh, 100,000 cells. From there, they were able to narrow down potential dam sites. And from the potential dam sites, they superimposed a hypothetical dam structure and inundated the hypothetical structure. And from there, they were able to calculate the potential reservoir volume. All right, so it's quite a convenient method. All right, so I didn't discuss all the details of the paper, so I just showed what can be done using remote sensing data for selecting dam sites. There are a lot of criteria and methods used in selecting dam sites. All right, so anyway, let's move on to the groundwater resources. So let's talk about aquifers and wells. So I assume that you have taken your hydrogeology class, so I won't be discussing things here in detail. So basically, aquifers are soil or fractured rock which are permeable and porous, and they store and allow economic extraction of water. So the key word in aquifers is the economic extraction of water. So this is a relative definition actually, strictly speaking. The same way we define ores or minerals are all about minerals that can be extracted economically. Anyway, groundwater or aquifers benefit from, or rather, groundwater are actually better than surface waters because, in terms of water quality, groundwaters are actually naturally filtered, okay, by the porous media. And there are many ways to harness or abstract water from aquifers. You can use water wells. If your site has springs, then you can install spring boxes. And in exotic cases, like in Africa, where they have relatively deep water tables, what they do is they construct underground dams that impound the groundwater, which raise their local water table so they can easily draw out water from that site. Now, note that when we are talking about water supply using groundwater wells, we are not just talking about single wells here. You may note that the pumping rate of aquifers may be bottlenecked by the transmissivity of the aquifer. This means if the aquifer is too thin or it has relatively low permeability, you can only extract so much water from a single pumping well. And in this case, you might want or you might have to design a well field with multiple wells extracting the groundwater. Now, in the Philippines, the largest groundwater well field so far is the Laguna well field, which has 20 deep wells, and it has also water reservoirs. Okay, so this facility can supply 100 million liters of water per day. It's quite a large facility in Laguna, and it's being managed by Laguna Water, a subsidiary of the Manila Water. Now, sorry, sorry. Now, wellfield considerations. Basically, we just have to make sure that the wellfield production or pumping rate is enough to meet the demand. Now, of course, it's not unusual to have fluctuations in the demand due to the dry and wet seasons, and it can be mitigated by setting up water reservoirs like storage tanks. All right. And note that the typical demand for water in the US, for example, is 400,000 to 2.6 million liters per day for small to medium sized communities. And for individual homes, it ranges from 6,000 to 26,000 liters per day. So note that this might be a little bit higher than in the Philippines because in the US they have large amounts of land and they have large agricultural areas per capita, meaning each person in the US tends to have a much bigger agricultural land to manage, hence their large water consumption. For example, in the Laguna groundwater well field, uh, it is estimated that they will be allocating around 1,000 liters per day per household. All right, so that's 1,000 versus 6,000. Okay, so that's a big difference. All right, so note the limits of groundwater extraction per well field or per well. The drawdown should not exceed 50 to 60% of the aquifer saturated thickness. So more or less half of the saturated thickness of the aquifer is you're only allowed to extract half of the saturated thickness of the aquifer. And then on a watershed management level, if we are to follow the principle of sustainable yield, the total groundwater extraction from all the wells in the whole watershed should not exceed 60% of the watershed's groundwater recharge. All right, so basically we take the annual groundwater recharge of the whole watershed. You can do that using hydrologic budget calculations, and from there just multiply that by 60%, and basically you shouldn't be drawing out more than 60% of the groundwater recharge for the whole watershed. Now, other considerations for the well fields. There's one important phenomenon that we should take note of is that multiple wells in close proximity tend to have an influence on each other. All right, so as you can see here in the figure, we have a well field, all right, of this I think 5 wells. As you can see in the plan view on the bottom left of the figure, you have 5 wells, you have 4 wells on the outer area and 1 central well. Alright? So if you will we are to we are to sketch or illustrate the drawdown of the system of wells. The solid line here is the total drawdown. Alright? That is caused by the well at that same location and also by wells in proximity that are influencing the drawdown. So in short, if you have other wells in proximity, they help pull down the drawdown. They help aggravate the drawdown at that well site. Okay? So basically, this main drawdown here is a total of all the drawdowns. Alright, this is the drawdown from the well in Q3, and this is the drawdown caused by well from Q2, and this component of drawdown is coming from the well from Q1. Alright, so they all superimpose their drawdowns on each other, and that should be accounted for in the wellfield design. Now alright, now this is how we design or calculate the number of and spacing of wells in a well field. So the first step is to determine the pumping rate QW at each well that would cause a drawdown equal to 1/2 of the allowable drawdown. Okay, so so we just look for the pumping rate that will correspond to half of the allowable drawdown. And this can be done using the Thies equation, assuming a pumping time equal to 1 year. Alright, so this is done to budget the allowable drawdown as follows. So note that the drawdown at the well point location due to the well's own pumping will be budgeted for around 50%. And the other 50% of the budgeted drawdown will go to the drawdown cost by the interference of other wells, boundary effects, and other well losses. So I reflected that in the figure. So if this is the allowable drawdown, half of it will be the allowable. So this will be broken down into two components. One half of it is due to drawdown due to interference of other wells and other losses and other boundary effects. And the other half is allotted for the drawdown due to the well itself. And then the second step, sorry, the second step is to determine how many wells do we need. So from step 1, we calculated the pumping rate of each well. So now we look at the actual demand requirements. So the demand will have a required pumping rate. So what we do is we divide that demand by the pumping rate of our individual wells. So we will get a number, we round it off to the nearest integer, and that would be the number of wells that we need to cater to the demand, to the water demand. Step 3 is to calculate the distance or the spacing of the wells from each other. So what we do here is we start with the central well. So the central well will always have the biggest drawdown. This is because it has a lot of other wells on its periphery. Okay, so the central well will be subject to a lot of interference from other wells. So what we do here is that we solve for the distance that would limit the interference drawdown to just 50% of the allowable drawdown, or less than 50% of the allowable drawdown. So for example, if you have four wells, so say you have four wells to design, that would mean that you will have a one central well and you have three other wells on the periphery. And say for example that the 50% of the allowable drawdown is 6 meters, then we should design the three other wells so that they should be far enough so that their interference drawdown being exerted on the central well will be or will total to just 6 meters. Okay. uh, all right. So there is an equation for that, and we will discuss that in detail in the exercise, which I will be sending on the next week. All right. Now, going back, note that in a detailed design analysis, other site characteristics are considered. So the wells should be inside the property boundaries. You should also avoid existing pipe networks. And typically, the wells should be as close as possible and parallel to the recharge boundaries, such as rivers and canals. All right, so this is to maximize the recharge and minimize the drawdown. Okay, when the well is near a recharge area, you more or less have minimal drawdown. And also, as much as possible, make it far away from impermeable boundaries. The reason being is that if your well is near an impermeable boundary, your pumping rate will be limited, and you can also induce a lot of drawdown. All right, because you're essentially not getting any water from the side near the impermeable boundary. Typically, production wells are spaced at least 75 meters apart. But of course, when we are doing design, this could be much larger. So of course, we'll be talking about the method in detail in the exercise. Now let's move on to the wellhead protection areas, or WHPA. Wellhead protection areas are essentially buffer zones or areas which have a regulated land use to minimize the introduction of contaminants. In other words, these are areas that are typically designated as reserves or no build zones, no residential houses, no factories, nothing whatsoever, to minimize the introduction of contaminants in the vicinity of the well. And WHPA is the most effective way to protect your wells from contamination. And the typical contaminants of concern are your organic chemicals like solvents, pesticides, and petroleum products, and also viruses. So, for example, the Hong Kong SARS in 2003 spread out from patient zero through a toilet sewage. All right, so you can imagine, basically one of the first infected patients of the Hong Kong SARS. He basically pooped on the hospital toilet, and his fecal matter had viruses, which then reached the sewage and spread out uh, throughout Hong Kong from there. All right. So what you're seeing here in the figure is an example of a watershed uh, wellhead protection area. All right, and shaded here are different distances depending on the travel time. All right, if you want to the contaminants to travel 25 years before reaching the well, this should be the distance. If you want them to travel 5 years, this should be the distance. If you want them to travel 2 years before reaching the well, this should be the distance, and so on. Now note that contaminant concentrations in groundwater are reduced via what we call attenuation. And in turn, and attenuation has a lot of component processes. You have your dispersion, which involves physical dispersion due to velocity gradients and also chemical diffusion due to concentration gradients. So, in layman's terms, contaminants tend to spread out to areas with faster velocity, groundwater velocities, and they also tend to diffuse into areas with lower concentrations. So, contaminants really generally tend to scatter around. And then you also have the decay, and these are the chemical and microbial processes which transform or consume the contaminant. And lastly, we also have sorption and filtration. Uh, this this pro these processes involve the attachment of contaminants on the surface area of your soil grains. This is really quite common in uh, oily contaminants. Now note that the effect of attenuation is typically a function of time, meaning the longer the contaminants have to travel or have to stay before they reach the wellhead, the better. Okay. Now, you have multiple possible approaches in delineating your wellhead protection areas. You have your distance, your drawdown, your time of travel, and your flow boundaries, and also the assimilative capacity. The distance is all about the distance and drawdown criteria are mostly arbitrary criteria. All right, they don't really relate so much to the actual contaminant transport processes. So we are essentially just guessing where we are using a distance and drawdown criteria. Now, the other criteria is the time of travel, which is more or less the widely used criteria or criterion. And the time of travel criterion, all right, so we just model the advection and or the transport and the decay process of the contaminants. So this method neglects dispersion. So it's actually quite conservative because because dispersion actually speeds up the attenuation process. So if you don't put in dispersion in your calculations, you are actually calculating a attenuation rate that is much slower. Okay, so it's actually quite conservative. All right. And yeah, the typical thresholds for time of travel is around 5 to 50 years. Time of travel method in here, we usually convert the time of travel into distance, as you have seen in the previous figure. The next is the flow boundaries. Alright, so this provides the highest level of protection. So what we do here is we account for the actual hydrogeological conditions, like where is the flow actually going, if there are actually aquifers or aquicludes that are protecting the aquifer area, we should include that in the boundary. And the last is the assimilative capacity. So this is more or less a comprehensive method which models all the contaminant transport processes. So this requires a lot of technical expertise. Okay, but of course this is a really precise method. Alright, let's resume. This is the time of travel approach for wellhead protection area delineation. So what we do here is we calculate the travel time from the potential contaminant source to wellfield. And we are essentially talking here about the travel time that will allow for sufficient attenuation. Okay, so this is about travel time for sufficient attenuation process to occur. And travel times are commonly determined by using a groundwater flow model with particle tracking with advection. So by advection, we model the groundwater seepage velocity, and by particle tracking, it means that we incorporate the decay process. Okay, so note that the main consideration here is to know how much time do we need to uh, to cause the contaminant to decay to safe levels. Okay, so the keyword here is decay, enough time to decay to safe levels. Alright, so yeah, as discussed earlier, we can peg the travel of time to the time for the contaminants to decay. And note, for most biological and chemical processes which involve a decay, they typically involve a decay rate which is proportional to their concentration. So it means that the higher your concentration is, the faster your decay rate will be. And this is what we call a first order process. All right. A first order process or a first order reaction, all right, has a rate that can be estimated using the equation in form of C divided by C naught is equal to E raised to negative lambda times T, where C naught is your initial concentration, C is your concentration after time T, and T is the time elapsed between C and C naught in days. And then your lambda or your half-life constant or your decay constant is an exponent parameter which can be obtained from literature. or it can be calculated from the half-life time or T50 of your contaminant. Now from there you can obtain how much time do you need for your contaminant to reach your safe concentration levels. So you now have your time of travel, and to make it practical and enforceable as a wellhead protection area, all we have to do now is to just calculate the distance, all right, that is involved to allow that time of travel to occur. So for example, if we are looking for a if you are looking to construct a let's say for example a factory near a well, all right, so we take a contaminant from the factory and then calculate the time that the contaminant will take to decay into safe levels. So once we have that time of travel, we plug it into to the well continuity relation. All right, so to get the distance that is necessary for that time of travel to occur. Okay, so the equation is R is equal to square root of Q sub W times T divided by pi Bn. So Q sub W is your pumping rate in cubic meters per second. Time is T is time in seconds or your time of travel. R is the radius distance from well to the contaminant source. And B is the saturated aquifer thickness. And N is your effective porosity. Alright, so whatever value you get, whatever distance you get, that is the distance that would allow for enough time for your contaminant to decay into your safe levels. And that would be the distance or the radius distance of your wellhead protection area. Alright, so now let's move on again to the water resources of the Philippines. Alright, and this is the water usage and classification uh, guideline used in the Philippines from the DNR Administrative Order number 34 series of 1990. Now, note that when you are working in the government or you're dealing with people in the government, most of the stuff that they do is dictated or controlled by your administrative orders, memorandum circulars. Okay, so meaning they just tend to follow by the book. So everything they do, everything they design has to be guided by documents that are in writing by their respective departments. So in short, be aware of these documents, all right, like administrative orders, memorandum circulars. All right. Anyway, going back, the this classification is applicable to fresh surface waters and also coastal to marine waters. And water classes relate to usage. So water classes dictate what water can be drinked, what water can be used for swimming, what water can be used for industrial purposes. And each water class has a corresponding water quality parameters like pH, dissolved oxygen, coliform content. Okay, so coliform is It's a bacteria that is mostly coming on from sewage, as pictured on your bottom right. So this is the overall classification scheme. So we have a classification scheme for fresh waters and marine and coastal waters. So the water usage defines what can we do with these bodies of water. Okay, how can we use them? And then the next part of the scheme is the minimum criteria for all surface waters. So these are all the non-negotiable criteria. All right, uh, that must be applied on all surface waters in the Philippines. Okay, so we should always ensure that these criteria are followed to ensure the preservation of our surface waters. All right, and then the next part three, is the water quality criteria for fresh waters, and that includes the conventional pollutants and the toxic substances. And then part 4 is the coastal and marine waters criteria, which also has conventional pollutants and your toxic pollutants. Now, I won't be discussing or be reading verbatim all these definitions. They're too freaking boring to read. So what I did here is that I just summarized and laymanized these definitions. So for water usage, Class A fresh water is essentially a body of water that is really, really clean and inhabited, and this includes most of the drinkable swim waters. All right, but although in the water classification, these waters have to be checked, all right, by the national standards for drinking water first to see if there's any form of disinfection that has to be done. Okay? And class A is mostly water that you can't really drink, but can be drank after filtration and other water treatment. Class B water is mostly for swimming and other recreational purposes, skinny dipping if you want. Class C is for fisheries, for boating, and also for dumping of clean wastewater from factories. Okay, so if you have clean water from a factory, you can dump your water in a Class C body of water. Class D is mostly for water for livestock and animals and for cooling of machinery. This is an example of a Class AA water. This is the Bugang River in Antique. Oh, sorry. I think this is the Ulian River in Iloilo. All right. So apologies for the correction. So the Ulian River is a Class AA, Class AB, Class C. All right. If you look at the different parts of the river, as per the Environmental Management Bureau. Now let's move on to the coastal and marine bodies of water. Class A is for shellfish and commercial harvesting of those shellfish. Also includes your marine parks and marine reserves, and also includes your tourist zones like diving spots. Class B is mostly for bangus, fish culture, and other related fishes, and also for swimming and other recreational activities. And then Class C is for mangroves and marshes and boating activities. And then finally, Class D is for cooling of machinery and other purposes. This is an example of a Class SA Okay, so this is the two Bataha Reefs in Palawan. This is a national marine park. Now, these are the minimum criteria for all surface waters. So again, I just laymanized all these jargon. So basically, all surface waters should have no foul-smelling deposits, no floaty or oily stuff, no nasty smell, nasty taste, or weird color, no toxic stuff, no stuff that can cause cancer, mutations, birth defects to wildlife and humans, and anything else that can cause danger. Okay, so stop asking me. uh, that's my interpretation of the last statement. So, statement 6 is that any uh, any discharge or substance that pose a serious danger to public health, safety, or welfare. So, uh, basically anything, any substance that's just dangerous. So this is a super duper blanket statement that can mean anything: nuclear bomb, grenade, I don't know, anything that's dangerous. Again, continuation of the criteria. What all surface water should be free from uncomfortably cold or uncomfortably hot temperatures to humans, fishes, and plants, and also temperatures that are too hot or rather hot or cold enough to cause harm or death. All right, so those are the criteria for all surface waters. Now I will be just discussing the criteria. Okay, so instead of discussing the criteria for fresh waters and the marine waters, I'll be just discussing the criteria or the tests used, all right, in both water quality criteria. So these are the common pollutants. I will define them one by one. Color or PCU is the platinum cobalt color scale, which ranges from 0 to 500, where 0 is a clear distilled water and 500 is a yellow tinted polluted water. So 500 is yellow, 0 is clear. Dissolved oxygen, typically you get low dissolved oxygen in stagnant or non-moving waters. The next is your 5-day biochemical oxygen demand, or BOD. This measures the oxygen requirements of your aquatic organisms in the water. So more or less, the DO should not be too small relative to your BOD. Otherwise, you will have your organisms dying in the water due to the lack of oxygen. The next is the total suspended solids. These are particles that are larger than 2 microns. So note that human hair is 50 microns in diameter. Next is the total dissolved solids. These include inorganic salts, organics, and other compounds which affect the taste and staining of water. And this typically include calcium, magnesium, sodium, potassium, and other cations and carbonate, hydrogen carbonate, chloride, sulfate, and nitrate anions. Surfactants or MBAS. This test is to detect presence of surfactants such as detergents or foaming agents. Other criteria is nitrate as nitrogen. All right. Note that nitrate can cause birth defects, and nitrate can come from fertilizers, livestock, sewage, and dump sites. Next is phosphate as phosphorus. Note that excess phosphate can uh, is essentially food for algae, and too much phosphate can cause algal blooms, which can suffocate all the fishes in your body of water, resulting in fish kill. And phosphate can come from sewage, chemical manufacturing, vegetable and fruit processing, and paper manufacturing. And then you also have phenolic substances as phenols. Note these are your highly toxic substances which can inflict severe and long lasting effects on humans and animals. And these can come from industrial, agricultural, and domestic activities. And you also have your coliforms, which are bacteria coming from the digestive systems of your animals and humans, and they can come from sewage and livestock industries. And finally, you have your chloride, as Cl, which affects the potability of water. You can have chloride from saltwater intrusion or mixing, also from agricultural and industrial wastewaters and sewage. Alright, so now we also have our toxic pollutants, which are generally ranging from effects that are persistent to effects that are severe on humans and animals. Alright, so for detailed discussion of toxic pollutants, you can refer to UA 2018. It's an excellent book, a guidebook on contaminant investigations, and it includes an extensive discussion on all the contaminants that are typically encountered in water. Now, these are the criteria for freshwaters. So the table on your left is the criteria for conventional pollutants, and the second table is the criteria for toxic substances. All right, so I won't be discussing that in detail. I already discussed the individual criteria. And then this is the criteria for coastal and marine waters. Again, table on your left is for the conventional pollutants, and the table in your right is the criteria for toxic substances. All right, so we discussed the water body usage and classification. So again, the water body usage and classification, we use it to classify our bodies of water, and we also use it to determine what to do, or what can we do with that body of water that we have. Like, can we use it for water supply? Can we use it for swimming? And so on. Now, we also have this Philippine National Standards for Drinking Water of 2017. Now, this is all about drinking water, alright? So, this is all about the water that is reaching our faucets, the water that we get from the water filling stations, the water that we get from the bottled waters from groceries. So, this is more of a consumer uh, consumer industry related standards, but I'll just discuss it briefly for you to be familiar with this standard. So the purpose of this standard is, of course, to just protect the consumer health. And the standard applies to all drinking water service providers, government, private, bulk water suppliers, water filling stations, water vending machines, ice manufacturers, food establishments, buildings like hotels, condominiums, and other buildings that serve drinking water, water testing laboratories, and also health and sanitation authorities. Now, you have different tiers of water quality parameters. The most important, of course, is the mandatory water parameters. So these are legally enforceable, meaning if you break these parameters, you can get fined, you can land jail, you can get lawsuits, and so on. And then the tier 2 is the primary parameters. So these are site specific parameters and can be adopted as enforceable parameters depending on the site conditions. And then you also have your secondary parameters. So these parameters just show which contaminants that if they are present, they may make the water difficult to treat to make it potable. And last, you also have your emergency drinking water parameters. So note that in the event of calamity like earthquake, flood, landslide, the LGU in your area should be able to provide an emergency drinking water within 72 hours. Alright, so this is important. In case of emergency, the LGU should be capable enough to provide drinking water within 72 hours. And they should be at least disinfected uh, using the minimal standard procedures like boiling and chlorination. And in addition, they should be also monitoring the emergency water for chlorine and E. coli for 7 days or until the emergency ends. All right, and this is the mandatory drinking water quality parameters. All right, so you have your E. coli, arsenic, cadmium, lead, nitrate, color, turbidity, or the amount of light scattering that the water does. Note that a clear water won't scatter light a lot. pH and then dissolved solids. Now let's talk about the uses, management, and problems of the water sources in the Philippines. This is based on the Water Resources in the Philippines paper by Edward Lapong and Masayuki Fujihara in 2008. And I think this is a good overview of the status of water resources in the Philippines, although it's a bit outdated. This is almost, I'd say, 13 years old. Alright. Climate wise, the Philippines has an average annual temperature of 27 degrees Celsius, humidity of more than 70% throughout the year, so it's actually quite humid. You will feel this humidity once you start living outside the Philippines and move to a dry country. In my case, I lived in New Zealand for more than 2 years. When I came back in the Philippines, I couldn't breathe with the humidity in the Philippines. It's super duper humid. Also have high solar radiation. Also high frequency of tropical cyclones, approximately 22 to 24 per year. We also have a relatively high annual rainfall of 2,400 millimeters per year. But do note that 38% of that rainfall is coming from tropical cyclones, which is quite difficult to harness. And then we also have a runoff volume estimated to be around 257 cubic kilometers. Now, freshwater bodies. The surface waters, we have 59 major lakes, 421 river basins with a drainage area of more than 40 square kilometers, and 18 major river basins with a drainage area of greater than 1,400 square kilometers. And we have a total of 1,000 square kilometers of freshwater swamps. And then for subsurface waters, we have aquifers that cover an area of 50,000 square kilometers, and their storage capacity is around 251 cubic kilometers. And we have four major aquifers that comprise 67% of the total volume of all our aquifers in the Philippines. Now, in terms of fresh water supply, our surface waters have a potential to supply approximately 126 uh, cubic kilometers per year. And but if we look at our actual use, most of our use is actually dedicated to agriculture. All right, like three-fourths is used in agriculture, as you can see in Figure 2 in the bottom part of the slide. So 74% is used on agriculture. Although note that the economy of the Philippines, the agriculture contributes around just approximately one third of our economy. And then groundwater, the potential supply is approximately 20 cubic kilometers per year. And for the groundwater, the story is quite different. 63% is used for domestic purposes, meaning household supplies. Now, for extraction or abstraction of groundwater, most of the abstraction is done through private wells, which is common in rural areas for domestic consumption. And then our waterworks are drilled by the Local Water Utilities Administration or LUA for domestic and commercial purposes. So the bigger wells are drilled by LUA, and they help assist in setting up local water cooperatives, which are water supply companies that are more or less managed by the local government. And then we also have deep wells, which are drilled by companies for industrial use. And then we also have wells for irrigation, which are drilled by the National Irrigation Administration or NIA. Now let's move on to the future water demand. As per the study of JICA, the water demand in 2005 was 49 cubic kilometers, but this is expected to increase up to 86 cubic kilometers in 2025. All right, so that's almost a two times increase within 20 years. And note that our water supply is just around 100 plus cubic kilometers. Okay, so we can't or we shouldn't really grow that much. I mean, our population should probably stop growing too much, and we should stop reducing our water consumption. And then water usage by agricultural industry decreased by 11% from 1975 to 2000, although this also was matched by an increase in domestic and industrial use. In terms of freshwater availability or the fresh water that is actually being extracted and available to every person in the Philippines, our freshwater use is just 11% of our total water resources. And our total withdrawals as percentage of actual renewable water is just 13.3%, which is actually quite a good thing. So as a result, we have a relative low freshwater availability per capita at around 1,907 cubic meters. All right, as opposed to the worldwide average of 7,405 and the Asia average of 3,668. So we are lagging behind our Asian peers and by a lot in terms of worldwide averages. Now, in terms of irrigation use, note that the agricultural sector, their use of water mostly goes to irrigation, and you're so damn fucking inefficient when it comes to conveying water. Like, we're losing 60% of our water in irrigation during the conveyance of the irrigation water. Okay, so 60% loss. And then reservoir dams, our total dam capacity in 1995 was 4.75 cubic kilometers, and that comes from 54 small dams and 6 large dams. Although note that 80% of that capacity was coming from the 6 large dams. Okay, so large dams contribute a lot to our dam capacity. All right. So in the Philippines, a dam is considered large when your capacity is more than zero point 0.5 cubic kilometers and the structural height is more than 30 kilometers. Though this is quite weird because the International Commission on Large Dams, they define a large dam as a dam with a height of more than 70 meters. All right. This is quite weird actually. Anyway, potential sites for major dams. We have 438 potential sites for major dams and 423 potential sites for smaller dams. Now let's look at the management sector. Okay, so you can see here how much our management of water is so messed up. So we have so many government institutions that are involved in the water management sector. I mean, I can't even count it with my fingers. So you have your EMB, FMB, Bureau of Soils and Water Management, National Power Corporation, PNOC, NIA, DOE, and WRB, DOH, DPWH, NEDA, and CIP, and even the Water Crisis Commission. Okay, so this is a dizzying list of government institutions. So DNR is responsible for the management, conservation, and development of forest lands and watersheds, as well as maintain the water quality. The BWSM is about the management of soil and water as vital resources. So it's quite how do you differentiate that from the role of DNR? It's quite not really super duper clear. They also have a role of design and construction of small water impoundment dams, so that's quite clear. NPC has the authority to take water from any public stream, river, or any body of water for power generation. Okay, so they have complete jurisdiction over the watersheds that surround the reservoir plants or projects. So again, this is quite overlapping with the role of TNR, who is supposed to manage the watersheds. Okay, PNOC, I mean surprisingly, the Philippine National Oil Corporation also has the jurisdiction, control, management, protection, development, and rehabilitation of watershed reserves. So again, this overlaps with the NPC and DNR's roles. You also have NIA, whose role is to improve, construct, and administer all national irrigation systems of the country. So this now overlaps a bit with the mandate of the DABSWM. Okay, so who is also in charge of in charge of construction and maintenance of small water impoundments, which are actually part of national irrigation systems. You also have DOE, which is supposed to allocate reforestation, watershed management, health and environment enhancement fund. Which this again conflicts with other agencies. DOH is to set is to set quality standards for water testing, treatment, surveillance, and sanitary practices. So this is quite sort of overlaps with DNR. And then DPWH has to set technical standards for engineering surveys, design, and construction of level 1's water systems. And then NEDA is in charge of the policy making and infrastructure coordination of activities of various sectors. So this NEDA here is more or less the coordinator of all these mess of institutions. So NEDA has to talk with all these institutions to ensure that they are in sync with each other. Okay. And then you also have your National Commission on Indigenous Peoples. So once you have any projects or watersheds that are under the ancestral domain, you have to talk with your IP groups. And then you also have your Water Crisis Commission, which is supposed to address any water crisis. Okay, so that includes waste of water and pilferage of water. Okay, so these are all the national institutions. Alright, so this is the national level, and this is the local level. So you have your LGUs, your LUA, and your Maynilad, MWSS, and Manila Water. So LGU is in charge with community-based forestry projects with areas that are not exceeding 50 square kilometers. And then LUA is to own and operate water supply and distribution systems for domestic, industrial, municipal, and agricultural uses. So this is somehow quite clear. So you have LUA for everything else that is bigger than 50 square kilometers. And then you have Maynilad, MWSS, and Manila Water for the water supply of Metro Manila and nearby suburban areas. So as you've seen in the previous slides, you have Laguna Water that is being operated by that is essentially a subsidiary of Manila Water. So as you can see, Laguna, Rizal, Bulacan, these areas are already slowly being integrated into the Greater Metro Manila area. All right. So in consequence, you have your Maynila and Manila Water expanding their coverage in those areas. Now, the problems and emerging issues. First is the fragmented management and weak institutional framework. So if you actually count the number of agencies and departments dealing with those water management functions, there are more than 30. So you have 30 departments, agencies, and whatsoever, but uh, you don't actually have one institution that is actually managing river basins. Okay, there's none. So this is quite a common pattern in the Philippine government, like in the geohazards. You have two agencies that manage landslides. You have PVOX for earthquake-induced landslides. You have MGB for rainfall-induced landslides. Informally, you have DPWH for mitigating landslides and slope failures. Okay, but again, you still have you still tend to miss out certain geohazards. So same here happens with the water resources. All right, so the implication of this is that you have entity responsible for planting trees in a watershed area, but another agency is authorized in granting a permit to cut the tree. So doing one thing might mean that you had to talk to two or more agencies, okay, just to get moving. Okay, so this is a bureaucracy nightmare, and okay, so I think this is one of the things that contribute to the corruption in the Philippines. Too much bureaucracy. Another problem is the lack of water allocation formula, meaning we're not really have a defined rule on how to allocate how much water do we give to this area, how much does this community get, okay, for water. So we have increasing population, we have a worsening pollution, we have poor infrastructure, we have droughts. So there is a constraint in water supply, and there is a conflict in rights over the water supply. Okay, so you can see in the recent shortages in the water supply of Metro Manila last December 2020. So there's a lot of finger pointing between like your MWSS, your Manila Water, Maynilad. Okay, so there's a lot of issues here, and we're not really budgeting, or we're not really setting clearly how much water should go to whom. Okay. I also read somewhere that there's still an ongoing conflict between NIA and the MWSS, because historically the Angat Dam has most of the water of Angat Dam was going to NIA, was going for NIA for agricultural use. And then over the years, they had to grant more water rights to MWSS for the urban populace. So NIA and MWSS had a deal where MWSS had to buy the that share of water that MWSS will get from NIA. But until now, I think it's still an unpaid. It's still unpaid. Okay, so yeah, there's a lot of conflicts all over our water resources. And then you also have a weak water use regulation and enforcement. So all in all, if we will look at the chain of command, NWRB, or National Water Resource Board, is supposed to be the sole authority that allocates water rights. Okay? By mandate, NWRB is supposed to be overseeing everything that is related to water resources in the Philippines, but they just don't have enough manpower. They don't have enough resources to properly check everything that's happening. You can't even process properly water permit applications. So what happens is we just delegate everything to other agencies. And this has resulted really in really controversial decisions. Like recently, there's been a lot of local water cooperatives that are being bought out by private water entities, particularly Prime Water by the Villars. They've been buying a lot of local water cooperatives. If you start searching the internet, uh, it's going on a quite an alarming rate. All right. All right. So that ends the all the lectures for the water resources module of this course. For next week, we will be discussing the exercise. Okay, so we'll be just having one huge exercise for the whole module. Alright, so thank you for listening. If you have concerns, just message me in Blackboard. And here are the references. Chin 2013, this is a comprehensive text, alright, for all the stuff, all the calculations that you have to do to develop water resources. And I also listed here the relevant administrative orders and national standards. Also listed here is the paper Fesselbon and Blanco. And I also included the Bible on Dams by Fell, McGregor, and Stapleton, and Bell and Foster. Alright, and also UWE for the contaminated site assessment guidelines. Alright, so that concludes this lecture.